video on equilibrium. Okay, remember we were talking about chemical equilibrium, and in the last video we did give an introduction to chemical equilibrium. We talked about dynamic equilibrium, the characteristics of the dynamic equilibrium, and we gave 3 characteristics. And then we did talk about the Chatelet's principle, okay, which is a very important principle that governs equilibrium. Okay, so before we continue, you can always consider subscribing, okay, liking, sharing, and commenting on the videos that we share with you guys. Alright, now in this next part of the video, I'm going to be talking about factors that affect the equilibrium, okay, the factors that affect the equilibrium. Now we're going to be talking about 2 things here. You're going to have what we call the equilibrium constant, okay, you're going to have what we call the equilibrium constant, okay, and you're going to have what we call the equilibrium position. Now these 2 things are very different. Okay, the equilibrium constant and the equilibrium position, alright, are 2 different things. So the position of the equilibrium, okay, will depend on whether it is a forward reaction which is being favored or it is a backward reaction which is being favored. But with the equilibrium constant, okay, it depends on the value, on what is happening, but it depends on the concentration of the products at a particular time and that of the reactants. That's what affects the equilibrium constant. So there are some factors that will affect the equilibrium constant, and some will not affect, and some factors that will affect the equilibrium position, but some will not affect. Okay, so there are 3 main factors that can be changed here. You have temperature, okay, temperature, you have concentration, okay, temperature, concentration, and pressure. So these are the 3 factors which we're going to be discussing about. Now just imagine you have a reaction, okay, that reaction is let's say N A plus NB in a reversible fashion to give, let's say, let me write like this, PC plus QD. Okay. Now here, if I increase the concentration, okay, let's talk about concentration first. Now if I increase the concentration of either A or B, the reaction, the equilibrium position, okay, is going to shift to the right. Okay, if I increase the concentration of P, of C or D, the equilibrium position will shift to the left. So if I increase A or B, more of C and D will be formed. Or on the other hand, if I increase C or D, okay, more of A or B will be formed. Alright, that's the simple thing about concentration. Now the second one is temperature. Okay, now temperature will depend on either if the reaction is an exothermic reaction, which of course they usually represent they usually give a beside equation as delta H equal to negative. That's for an exothermic reaction, exothermic. Okay, or if the reaction is endothermic, okay, the energy change is positive, so endothermic. Okay, so for an exothermic reaction, okay, for an exothermic reaction, increasing the temperature rather favors the backward reaction, and decreasing the temperature favors the forward reaction. Okay, that's it. Now, for an endothermic reaction, the reverse occurs. When you increase the temperature, the forward reaction is being favored, and when you decrease the temperature, the backward reaction is being favored. So you see, temperature affects the reaction based on if the reaction is exothermic or endothermic. Now for pressure, okay, pressure is going to depend on if it's actually relevant, okay, in pressure in gaseous systems. For example, in the Haber process where you have the formation of ammonia. Okay, so when you increase the pressure, it favors the side with the lowest number of moles, and when you decrease the pressure, it favors the side with the highest number of moles. What am I saying? If I increase the pressure in the Haber system, okay, what happens is that more of ammonia is going to be formed, so the equilibrium position will be shifted to the right. Okay, now if I decrease the pressure, okay, since the left hand side has more number of moles, that is 1 plus 3, which gives us 4 moles. So here we have 4 moles, and this one we have 2 moles. So when I decrease the pressure, it favors the side with the highest number of moles. Okay, so the backward reaction is going to be favored, or the equilibrium will shift to the equilibrium position will shift to the left. But if I increase the pressure, the equilibrium position is going to shift to the right. Okay, that's how pressure affects the rotation system. Now, there is one other thing, catalyst, a catalyst, okay? Now, a catalyst simply increases the rate at which equilibrium is attained, alright? It does not affect the equilibrium position, right? One very important thing you should know, okay? The catalyst does not affect it does not affect the equilibrium position, okay? It affects the rate at which equilibrium is attained. So, it means if equilibrium was supposed to be attained, let's say in 10 minutes, okay, it makes equilibrium to be attained maybe in 2 minutes. So it simply increases the rate at which equilibrium is attained. Okay, just like you have an enzyme, for example, okay, in a system. So here I can have, let's say, this is enthalpy change. So this is enthalpy change. Okay, this is a reaction path. Reaction path. Now, say for example that a reaction normally was supposed to take this path. Okay, this is the reactants and these are the products. Okay, when you put in a catalyst, what happens is that the catalyst, alright, is going to make the reaction is going to decrease the activation energy, okay, and increases the rate at which it will be attained. So instead of the reaction going through this, passing through this path here, through path A, say for example, okay, the reaction is going to pass through path B, okay, which makes its equilibrium to be attained faster. So what it does is, okay, for this reaction, the catalyst decreases the activation energy, alright? So here you see the first activation energy, let's say EA, alright, is greater than the second activation energy, EB, alright? That's the role of the catalyst. So the catalyst does not have any effect on the position of the equilibrium. Now the next thing is, okay, the temperature is the only factor that affects the value of the equilibrium constant, which we are going to be seeing in the next video. Okay, so the equilibrium constant is being affected just by temperature. So neither concentration nor pressure affects the equilibrium constant. Okay, so if you increase the temperature, for example, okay, for an exothermic reaction, since it is rather the backward reaction that will be favored, okay, the equilibrium constant is going to decrease. Okay, so when you increase the temperature, the equilibrium constant, if this is the temperature, okay, when you increase the temperature, the equilibrium constant for an exothermic reaction, okay, is going to decrease, so it will decrease Kc. If you decrease the temperature instead of, okay, for an exothermic reaction, of course, the value of Kc will rather increase. Now for an endothermic reaction, it is the reverse. When you increase the temperature, okay, for an endothermic reaction, okay, it increases Kc because the forward reaction is being favored. So there are two things I've stressed on. The catalyst does not affect the equilibrium position, okay, and I said temperature is the only factor that affects the equilibrium constant. Okay, so we're going to be discussing about the different equilibrium constant in the next video, okay, and the relationship between the two of them, alright, and how you can approach questions. So thank you very much for watching the video. See you.